Hey everybody. I wasn't really sure what to call this video. It doesn't really have a concise theme like the other ones. These are just three really fun puzzles that I've found over the last couple of weeks that I had a lot of fun solving. And I'd like to go through them all and my solutions to them all, just because I think they're quite interesting. Now I've written all three puzzles here already, so if you are or aren't interested in some of them, you should feel free to skip them. I'm gonna do them in this order. So I'm going to start with the first puzzle, which is prove that every positive integer has a multiple comprised of only ones and zeros in base 10. So I'm talking about the digits ones and zeros. So like a number like, if I was to say 110, this would be an example of a number comprised of only ones and zeros. So we're going to prove that every positive integer has a multiple comprised of only ones and zeros. So we can start really simple. 1 is trivially its own multiple. In fact, every number is a multiple of 1, so I can just use itself if I want to. That's fine. Now 2, is there a multiple of 2 comprised of only 1s and zeros? Well, I mean 10 is a multiple of 2. 10's an even number, that's fine. Now what about 3? Let's think about 3. I believe we have... I'm just finding it hard to think of an example on top of my head. I want to say 1011, I think. Multiple of 3. There's definitely going to be nicer ones than that. Now, what I'm getting at is that this process is going to go on for too long, right? It's going to go on forever, in fact, because we've got to prove it's true for every number. So we've got to try and find a systematic reason why every number has to have a multiple comprising of just ones and zeros. So let's start by just thinking about one number. And let's make it like a slightly higher up number. Let's consider the number 7. N equals 7. And let's try and prove that there exists a multiple of 7 comprised of just ones and zeros. Well, I'm going to start by considering what happens when I just pack numbers up with ones. So we've got 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And I'm going to actually do exactly 7 of these. Now, if I check these first 7 numbers, we're going to consider what happens in the mod 7 space, which just means remainders when dividing by 7. So every number mod 7 is going to equal 0, 1, 2, 3, 4, 5, or 6. All of these values are going to be congruent to something mod 7. Now, if any of them were congruent to 0 mod 7, like say for instance, if this was congruent to 0 mod 7, we would be done, right? We would have found a solution because this is comprised of only ones and zeros. So that's the best case scenario, is that we've just found one. Now, if we haven't found one, that means that these all have to be congruent to something other than 0 mod 7, which means that I have values 1 to 6 to choose from. Now keep in mind, I have values 1 to 6 to choose from, and I have 7 things. Now we've talked already on this channel a little bit about the pigeonhole principle. Basically it says that if I have 7 items and only 6 buckets, and I've got to put every item in a bucket, one bucket has to have at least 2 items. Same principle here. I've only got 6 options, numbers 1 through 6, but I've got 7 places I've got to put them. So at least 2 of these 7 numbers is going to have a double up. Now, it doesn't matter where the double up is, but let's just say, for instance, it happened to be, maybe these 2 happen to both be 3. And I'm just going to fill the rest up with different values for the sake of argument. Let's say the double up happened here. This means that there have to be at least 2 numbers in this set that are congruent mod 7. So 1, 1, 1 is congruent to 1, 1, 1, 1, 1 mod 7. Now, if 2 numbers are congruent mod 7, that means that their difference is a multiple of 7. And you might see where I'm going with this now. because these two numbers have a difference that's a multiple of 7, I can subtract one from the other. I'm always going to take away the smaller one from the biggest one, obviously. So I'm going to end up with 1, 1, 1, 1, 1 minus 1, 1, 1, which would equal 1, 1, 0, 0, 0. So if this was the case, this number would have to be a multiple of 7. And this number is comprised only of 1s and 0s. So yeah, and that basically proves it. And hopefully you can see how this can happen for any base. And I'm now going to give an example of a general form for base n. Sorry, not for any base, for any value. So instead of n equals 7, let's just say n equals n. Whatever n is, doesn't matter. We're going to do the same thing again. We're going to consider n of these numbers. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I'm going to go dot, 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 dot. And then down here we're going to have like, I don't know, dot, 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 dot. A lot of ones, right? So the idea here is that I have n numbers. And we're going to consider congruency mod n. Now again, if any of these n numbers happen to be congruent to 0 mod n, would be done. I would have found a number which is all 1s, which fits the rule. Now if none of these were congruent mod n, they'd have to be congruent. If none of these were congruent to 0 mod n, they'd have to be congruent to, well, what are my options? Could be 1, could be 2, could be 3, blah, 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 blah. Could be n minus 1, or n minus 2, I'll say, and then it could be n minus 1. These are our options. Right, in the same way that for mod 7, the options were anything from 1 to 6. Here it's anything from 1 to n minus 1. The most important takeaway here is that there are exactly n minus 1 elements here. So I have n minus 1 elements, and I have n spots to put them, which means that once again, by the same principle, if I had all my values here, a, b, a1, this can be a2, this can be a3, a4, a5, and this all the way down, this here is an. Because I have n options, but only n minus 1 numbers that I can fill, that means that by definition, there must exist a pair of values, I and j, such that ai is congruent to aj mod n. Now, we know obviously that out of ai and aj, one of them must be bigger than the other one. So let's say, for instance, let's just say that ai has to be bigger, which is fine. That means that ai minus aj is going to be a number with a bunch of 1s at the start and then some 0s, and that number must have n as a factor, so n divides this number here. So if I wanted to write this number out, it would be 1, 1, 1, 1, dot, 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 1, 1, 1, 0, 0, 0, dot, 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 0, 0, 0. And specifically, we have j zeros and I minus j ones. And that's the proof. And I thought that was a really cool proof. So we've shown that this is true for every positive integer n. Cool. All right, let's go to the next one. So the next one is proving that the square root of 243 is irrational. Now, if you have any familiarity with number theory, you'll recognize that number as a special number. And it's got the special property. 243 is, of course, 3 to the 5. It's 3 times itself 5 times. So it's prime factorization. It's just going to be 5 3s, which is quite a nice little fact about it. We're going to try and prove that it's irrational. So we're going to do a proof by contradiction as always. Let's assume it is rational and try and find a contradiction. So if the square root of 243 was rational, that means that there would exist some integers, a and b. Let a and b be integers that exist from the Cartesian product of the integers. I would be able to say that the square root of 243 equals a over b. Now, the square root of 243, it's the same thing as saying the square root of 3 to the 5 equals a over b, which is the same thing as saying, well, 3 to the 5 is the same thing as saying 3 to the 4 times 3. And you'll see why I've done this in a minute. This is going to become 3 to the 2 times root 3. Which is the same thing as saying 9 root 3. Now, if I divide both sides by 9, I end up with the square root of 3 equals a over 9b. Now, I don't really care about this 9b thing. All that matters here is that we've shown that 3 must still be rational, because 9b is just a number, right? Well, an integer rather. It's an integer over an integer. Square root of 3 must be rational. So we've shown that if the square root of 243 is rational, square root of 3 must be rational. So let's just start my problem again with the square root of 3. So we're going to go back to basics. The question has now become, for any a, b, we can express the square root of 3 as a on b. Now let's keep looking for that contradiction. Well, this would imply that 3 is equal to a squared over b squared. Which would imply that 3 equals, was implied that 3b squared equals a squared. Now, my very first video that I posted publicly to this channel, I believe, was about the proof that the square root of 2 is irrational. And you'll notice soon that this proof is basically the exact same. It goes on the exact same argument. Keep in mind here that a and b are co-prime. Co-prime. Co-prime means that their greatest common denominator, so the GCD of a and b, is 1. If they had a greatest common divisor that was greater than 1, we could simplify the fraction further. So when I say that a and b are co-prime, I'm just saying that this fraction over b is in its simplest form. If it was something like 14 over 7, I could simplify it further to 2 over 1. So that they're co-prime. Alright, so what we've ended up with is that 3b squared equals a squared. Because a squared can be expressed as 3b squared, it means that a squared must be divisible by 3. So we've established here that 3 has to be a factor of a squared. Now, let's consider what that means for a. Well, if 3 is a factor of a squared, I would like to try and argue that that means that 3 must be a factor of a. Now, this is something that I think algebraically you can kind of just know, but we will do the proof, because the proof isn't too bad. It's a proof by cases on the congruence classes of a mod 3. So a can either be expressed, a can be expressed in one of 3 ways. A could be represented as like 3 times some number, 3k. A could be expressed as some value 3k plus 1. Or a could be expressed as some value 3k plus 2. Or even 3k minus 1 might be easier, but we'll go 3k plus 2. These are our 3 cases. Hopefully you can appreciate that these cover all the grounds. These are the only 3 kinds of numbers that a can be. It's either going to be congruent to 0, 1, or 2 mod 3. So in all 3 cases, let's just consider what a squared would become. So in the first case, if a was equal to 3k, and it's important to say here k is just an integer. If a was equal to 3k, a squared would become 9k squared. Now, in this case, it's going to be 3k plus 1 all squared, which I should be able to do that in my head. That should become 9k plus 6k plus 1. And in this case, 3k plus 2 all squared, that should become 9k squared plus, I want to say 12k plus 4. Now the takeaway here is that in only one of these three cases is my solution divisible by 3. This here is divisible by 3, right? Because it can be expressed as 3 times some stuff. It's 3 times 3k squared specifically. This one here isn't divisible by 3 because it's 3 times some stuff. This all has a factor of 3 in it, plus 1. Therefore, it doesn't divide by 3. Same thing here. All this bit here is divisible by 3. So it's something divisible by 3 plus 4, which is the same thing as saying something divisible by 3 plus 1. Because I can write this as plus 3 plus 1. So again, it's got this plus 1 at the end. So the only way that a squared can be divisible by 3 is if a was divisible by 3. So, because those are the only 3 cases that can happen, that proves this claim here. So if 3 divides a squared, it means that 3 must have divided a. Alright, cool. So we've discovered that 3 divides a. Now, if 3 divides a, I can rewrite a in some form. Let's call it 3q. And again, q is an integer. So that means that I can say that 3b squared is equal to 3q squared. Expanding this out, I would get 3b squared equals 9q squared. Dividing both sides by 3, we get b squared equals 3q squared. So hopefully you can see the logic here. Now, we run into the exact same thing where b squared is now a multiple of 3. B squared is equal to 3 times some stuff, which means that 3 divides b squared. And by the exact same logic as before, if 3 divides b squared, 3 must divide b. So what we've established here is that 3 divides a and 3 divides b. Because 3 divides a and b, the greatest common divisor of a and b is not 1. A and b are not coprime. So a and b both have to be coprime and not coprime at the same time, which is a contradiction. So we found our contradiction, which means that one of our premises was false, which means that 2, 4, 3 has to be irrational. Because if it was rational, we could have two numbers that are both coprime and not coprime at the same time. And that's the proof. The square root of 243 is irrational. Cool. Alright, that one's all done. Final one. I think this is probably my favorite one. Does there exist a continuous function that maps reals to reals, which just basically means no imaginary numbers are allowed? Does there exist a continuous function from the reals to the reals such that f of x equals negative x? Well, let's check. So the most important thing here is this idea of continuous. Now continuous means something very specific in math. A continuous function, a sort of this more simplistic definition of continuousness in math would be, if I draw the function, I can't take my pen off the paper. So like if I had like this kind of thing going on, it would not be continuous anymore, because this point and this point don't continue on. So it's like one continuous thing like this, right? There are more formal definitions of continuity, but we're not going to worry too much about those in this proof. Continuous just means I can draw it without taking the pen off the paper. That's a fine way of thinking about it for this question. So does there exist a continuous function that takes a real and outputs a real? Now, if such a function did exist, we could prove it by just demonstrating it exists. So if we can find a function with this property, where f of x equals negative x, we would be good to go. It's important to state that this is saying for all x. That should be clear, but for all x. For all real x's, like this. So we can either give examples of the function to prove that it exists, or we need to find some clever reason why this function can't exist. So we're going to go down that route. Is there some reason why this function couldn't exist? Because I spent a long time trying to find the function that fit this property, and I realized that I couldn't. So why would that be? Well, I'm going to start by proving a property of this function called injectivity. Now, I don't remember if I've talked about injectivity on this channel before, but the idea of an injective function is there's only one way to get to every output. Another way of saying this is that for any A and for any B, if f of A equals f of B, that means that A has to equal B. So there is only one way to get to every output. There's no two inputs that give the same output. So if this was my input space, and this is my output space, and these were all possible outputs, and these were all possible inputs, but I had that this input maps to this output, and so does this input, the function would not be injective. So for an example, like f of x equals x squared is not injective, right? Because both -2 and +2 both give me 4. So I have two inputs that get the same output. So I'm going to try and prove that this function is injective, which is to say that this property here holds. Well, for two values a and b, let's say f of a equals f of b. So f of a equals f of b. Now, if this is true, then clearly f of a would have to equal f of b, because I'm just taking the function on both sides. There shouldn't be any problem with doing that to both sides, right? You do the same thing to each side, it's fine. Now keep in mind that f of a equals -a by our rule, by this rule here, and f of b equals -b. Oh, I keep losing my color. Is it this one? Yeah. If -a equals -b, timesing both sides by -1 gives me a equals b. So we've proven it. We've proven injectivity. We've proven that if f of a equals f of b, then a has to equal b. Now let's consider what injectivity means for this function. Let's bring back that plot. Let's draw some functions. So this one. Okay, this is an interesting function. Now notice that this function isn't injective. Why is it not injective? Because I have two inputs here that give the same output. So this can't be the function, right? And I won't go too much into this. There's a lot of theorems about this. I think there's one called the turning point theorem, something like that, that basically just tells us that if a continuous function is injective, it can either go only up or only down. And that's called being a monotonic function or monotone function. It strictly increases or decreases. And hopefully you can kind of see why, because as soon as a function goes back to a spot it's already been, like here, where it goes back down to this spot, injectivity is now failing because this input and this input yield the same output. So because the function is injective and continuous, we now have that the function is monotonic or monotone. The function's monotone, which means that it's either strictly increasing or it's strictly decreasing. Those are the two cases. So it's either think or dick. Those are the two cases. All right. Well, let's consider what both of these cases would mean. Let's say the function is strictly increasing. Well, if f of x is strictly increasing, then that would mean that the two values, let's say x1 and x2, if x1 was less than x2, So if this function is increasing, that means that if x1 is less than x2, then f of x1 would have to be less than f of x2. Now, for the same reason, and by the same logic, this would then also imply that f of x1 is less than f of x2, which means that the union of the functions, so f of x, would be increasing. Cool. All right. So that's one case. The other case is that f of x is decreasing. So we've covered this case here. Now, in this case, what if it's decreasing? Well, let's do the same kind of logic. If it's decreasing, that means that if x1 is less than x2, then f of x1 would have to be greater than f of x2. And for the same logic, by the same reason, that means that f of x1 would have to be less than f of x2. Now, notice how the signs flipped around this time? But because I did this process twice, I end up at the same point. I end up at f of x being increasing. So either way, f of x is increasing. But f of x equals negative x, which is decreasing. So we have a function here that is both increasing and decreasing. Now, a function can't do both. Therefore, we have a contradiction. Therefore, such a function cannot exist. So the answer to question 3, does there exist a continuous function of this nature such that f of x equals negative x? The answer is no, there does not. Cool, and I think that's everything for this video. So yeah, thanks for watching everyone, cheers.